Let's turn now to the subject, the important subject of space-time diagrams. So, what are space-time diagrams and what are they about? Well, fundamentally, space-time diagrams speak to a particular question, which is, how should we depict a series of events, right? That's something that we always do in our thinking about relativity. We're looking at various events from various perspectives. What is the most efficient way to depict that series of events? And we already have seen a variety of possibilities, right? You all know about movies, right? A movie shows event after event, and you just watch the film unfold on the screen, and that's the way the series of events is indicated. But earlier on, we encountered another way of thinking about a series of events. Let me show you this video again, because it really gets the point across really well. You can think about a movie like this, where you only see one moment at a time, and once it's gone, it's over. Or you can think about a series of events more as a kind of series of snapshots, a series of records which depict moment after moment after moment. Remember, we encountered this earlier when we were talking about the weirdness of changes in time over large distances. My point here is a little bit different. My point here is, if you want to be able to see a whole sequence of events at once, this is a good way to do it, to depict moment after moment after moment in one big collection of snapshots. Not literally snapshots, because we're talking about events at the same moment in time from one person's perspective, but this is a good way of doing it. Now, we saw another version of the same story when we focused in on a more, if you will, cosmic perspective like we have here, where again earlier we described how you can look at a series of events as a kind of series of now slices. We called them one moment after another moment after another moment. And the value of depicting events in this kind of way is that you're able to see a whole sequence of events at once. You don't lose a moment after it's on the screen and gone. And this is, in essence, really what a space-time diagram is about. It's a diagram, we will see, in which we are able to depict a whole sequence of events in one frame, in one geometrical picture, in one graph, if you will. So mathematically, we are thinking of time, if you will, as a new axis. Moment after moment after moment is being given a geometrical interpretation, right? You can think about this direction as the time direction. This direction is space. Each slice depicts what's happening at various locations in space. This axis is a time axis. So the way to think about that is we are including time as an additional axis, or if you will, an additional dimension is the language that we use, where we are looking at all of space at each moment of time, but including all of it in our pictures. Now, when we think about this from the perspective not of pretty animations, but when we put equations and mathematics to this, we depict events in much the same way, except by convention, for no really good reason, we typically choose the time axis to be the vertical axis, and we use these directions to be the spatial directions. Of course, we can't truly show three-dimensional space through time because we don't have enough dimensions to show that. We don't have four-dimensional screens, at least not yet, three space and one time. So what we do is we play the same game where we have two dimensions of space, or sometimes one. We'll simplify there as well. But we usually take the time axis to be vertical. So the picture then you should have in mind for our version of space-time diagrams will be something like this. So we'll have the x-axis, the y-axis. There is space at one moment in time. That's like one of the now slices. But now if we have the time axis going vertically, we have space at one moment in time, after another moment, after another moment, after another moment. Exactly the same kind of picture that we had a moment ago when we were looking at moment after moment in the expanse of the cosmos. Geometrically, though, mathematically, this is how we will encapsulate it. So we'll have x and y, say 2 dimensions of space, sometimes 1 to simplify things, and we'll generally take the vertical axis to be the time axis. Now, let me give you just a couple of examples so we can get a feel for how these space-time diagrams work. So example number 1, let's consider a flash of light that is spreading out from the origin. Let me say from the outset that we're going to choose our units so that the speed of light is equal to 1 in those units. And that becomes particularly useful because what it means is that when we look at a beam of light, the beam of light, let's say a flash goes on and it sends out light in all directions, the distance that the light will travel, of course, is velocity times time. If the velocity is 1, then the distance that the light travels numerically will be equal to the amount of time in those units that has elapsed, which gives us a particularly pretty picture for how we will depict in a space-time diagram a flash of light. Okay, so let's take a look at that. So here is a flash of light at the origin. It spreads out. Its radius is velocity of light times time, which in the units that we're using will just be r equals t. This is the movie version of a flash of light spreading out in all directions. What does the space-time diagram for that look like? Well, let's take a look at it over here. So here is the space-time diagram version, and notice what it has. It keeps each moment in time by having this additional axis, the time axis. So the movie, the light spreads out, and we only see the final moment in the frame of the movie. But here we have moment after moment after moment of the light spreading out more and more and more. And just to bring that point home, let me highlight the slices. One moment, the next moment, the next moment, the next moment. This is the unfolding of the spreading out of the flash of light over time. So you see the value of the space-time diagram is we see the whole history of the spreading of the light as opposed to just seeing where it got to at a given moment in time. So that's one example in which we have the space-time diagram version of a certain physical phenomenon. Let's look at another example. A flash of light in one space dimension where we'll see that the light goes along 45-degree lines instead of a 45-degree cone. We will simplify what we're doing, again, by only looking at one dimension of space, not two, as we were looking at in that picture. So what would the one-dimensional version of this be? So in one dimension, we have, say, a flash of light that will happen at the origin. That spreads out in one dimension, but the space-time diagram version, the light travels on these 45-degree lines. Again, the speed of light equals 1 means that we'll have equal amount of distance covered in equal amounts of time. So we have these 45-degree lines. This line over here is the history of the flash of light moving toward the right. This line over here is the whole history of the flash of light moving to the left. You see, the movie version, you're left with 2 dots in the final frame of the movie. The space-time diagram version, you've got more information there. You've got the full history at your disposal. Okay, so those are a couple of examples having to do with light, but you, of course, don't have to just look at light. We can look at a variety of other examples. Let's take a look at a few of them. Set up our graph paper here so I can make a nice, clean space-time diagram to work with. Of course, you don't have to have graph paper, but it's kind of nice in order to show what's going on. So here, say, are my coordinates, and let me label these guys now as one dimension of space, one dimension of time. So that will be the simplification that we'll use. And let's look at a variety of simple physical situations as depicted in a space-time diagram. So example number 1 is somebody who's sitting still at the origin. What will their trajectory in the space-time diagram look like? Well, since they're not moving through space, the only thing that happens is they move through time. Their trajectory in the space-time diagram would look like that. So that is someone sitting still at the origin. This is their history. They're always at one location in space, the origin, but they're there for various moments in time. Okay, let's look at another example. Let's say we look at firing bullets whose velocity is less than the speed of light. Well, what will that look like? Well, it's useful now for me to show you in this picture what a light beam looks like. So we've seen it already, but let's write it down. 45 degrees. I think that is 45 degrees. So that is the trajectory to the right of a beam of light. If something is moving slower than the speed of light, what will its trajectory look like? Well, let's choose another color. And if an object is going slower than the speed of light, then that means it won't cover as much distance in a given amount of time, which means the slope over here will be larger. That is, it's going more in time than it is in space, and that could be, say, a bullet whose velocity is less than c. What about another example? So here we have a round-trip journey. So someone goes off into space and comes back. Let's even assume that they don't have uniform velocity in either part of their journey. So let's say that maybe they go out into space and then they come back. Now, just so long as the magnitude of this slope is never smaller than 1, and it looks like I've drawn a little bit awkwardly over there, but you get the point. This would be someone who starts at the origin, turns around, and ultimately comes back. What about two laser beams that are firing at each other from different locations? Okay, what would that look like? So let's use yellow for a laser beam. And let's say we've got one laser firing from here. So a laser beam from there. Oh, that's kind of orangey. I don't really like orange for the color of a laser beam, so let's use yellow. So here is a laser beam, 45 degrees. I don't know, let's put it over here. And somebody else is firing from another location. Let's say they're firing, say, from over here, maybe, and their laser beam is going in that direction. So laser fire one direction, laser fire another direction. Again, we're getting the full space-time history in the space-time diagram. Final example, what if we look, say, at two people having a duel? They're firing bullets at each other. Well, let's use this for our first one. If someone is firing a bullet from some other location, let's say we use red for that, they too firing back in the other direction, and the slope here has to have magnitude that's bigger than 1, so it might look something like that. So maybe the two bullets hit each other at some location in space-time, right? Now look, you can get confused with these diagrams. It looks very two-dimensional, but what is going on here is we've got one dimension of space and two bullets are firing toward each other, right? So they will hit each other at some location. They're just moving in one dimension, but this is showing the full two-dimensional space-time history of the events in question. So that's the basic idea of space-time diagrams, and what we're going to look at next is how do we depict the space-time diagrams for two different observers moving relative to one another.